Hi, my name is Numan, and my teammates are Animal and Sean, and today we're presenting on the topic of graph theory. Graph theory was first introduced in the 18th century by Swiss mathematician Leonhard Euler, who was trying to solve the Königsberg Bridge problem. The problem involved traversing all the bridges you see here, but only once, and only once. Now, Euler determined that there was no solution to this problem, but it was the way that he determined it that led to the foundation of graph theory. He represented each of these land masses as vertices and each of these bridges as edges. Now, what are graphs? Graphs are essentially a set of points known as vertices connected by lines which are known as edges. The simplest example of a directed graph we know in computer science is a linked list. Some other examples in the real world are the web, where each document could be a vertex and they're connected to each other by references. In networking, each site send and receive messages of various types, which are edges. Program structures as well, where each class could be a vertex, and connecting each of these classes are edges, which is a possibility of a method of one class calling a method from another class. A little bit of terminology of graph theory are simple graphs, where a pair of vertices can only be connected by one edge, a multigraph, where a pair of vertices can be connected by multiple edges, pseudographs, where a vertex could have an edge connected to itself, and directed graphs, where we have edges with direction. Now, this terminology will be useful in the later problems we discuss.
Well, the first problem we're going to explore is sorting a dataset of unsorted values efficiently using a dynamic data structure for the values given below. Now here is a list of the data structures and their time complexity. We have array, stack, queue, singly linked list, doubly linked list, hash table, and a binary search tree. As you can see, a binary search tree is one of the most efficient implementations. Now before we begin, what is a tree? A tree is a particularly important kind of graph. This graph has n vertices or nodes, and it is a tree if it follows the following conditions. A tree must be an undirected connected graph. A tree must be connected by n minus 1 edges to the various nodes or vertices, and a tree must not have any cycles. This is the dataset we'll be using. Now, what is a binary search tree implementation? It's one of the most efficient data structures in terms of time complexity, insertion, deletion, searching, and etc. It's dynamic and sorts the values as they are added to the tree. Unique implementation that utilizes order relation for comparison of every element in the structure and places the values accordingly. And its efficiency in insertion, searching, and etc. is why it is used the most to build indexes and databases. What are the basics of a binary search tree? A binary search tree is composed of nodes, or vertices. Nodes contain a data element, a left and a right reference, such as the node A contains a left reference to B and contains a right reference to C. Topmost node is referred to as the root node, or in this case, A. Every other node is connected by one directed edge called parent. For the parent of D would be B. Now, what is the algorithm for a binary search tree? It has a few properties. The left subtree of the nodes only contains values lesser than the node's value. The right subtree only contains value greater than the nodes. Each of the left and right subtree nodes must follow the same principle, and there are no duplicate nodes. And as you can see with this example, when you're inserting 8 to a tree that already has a value of 7, it's compared to, and since 8 is greater, it's inserted to the right as a subtree. Now that we've gone over the algorithm, let's use the algorithm. The first value that's inserted is 63, which would make it the first node. 48 is the next value that's inserted, and since it's less than, it's inserted to the left. Since 73 is the next value that's inserted, and it's greater than 63, it would be to the right. And through this process, all the values in the dataset will be implemented. Well, binary search is very efficient in searching, indexing, due to the time complexity of O log n. And as you can see, it's very efficient.
One common problem in graph theory is how to find the shortest path length between two nodes on a weighted graph, and there are a surprising number of different ways to do this from a programming standpoint. First off, let's take a look at this simple graph and try to find the shortest path from node A to node E. It is pretty apparent that the shortest path is from A to C to B to E. but is not as obvious to a machine that can only look at one node at a time as opposed to looking at the entire graph. On the other hand, as graphs get more complicated, it becomes much harder for humans to immediately see that shortest path, and algorithms become a lot more useful. Some of the most common shortest path finding algorithms include Dijkstra's, A-star, Bellman-Ford, Floyd-Warshall, and Johnson's. All of these algorithms have different applications, whether they be for directed graphs, edges with negative weights, or node pairs, but all of them deal with finding the shortest path. In the two animations above, you see the visualizations of both Dijkstra's and A-star, in this case being used for autonomous robot navigation. As you can see, A-star is a much more efficient algorithm because it starts by going straight towards the goal then expanding outwards, which is due to the use of heuristics in order to guide its search. I would now like to give a quick rundown of Dijkstra's algorithm, which is one of the oldest and most well-known shortest path link algorithms. It is also the foundation for many of today's more specified path-linked algorithms. Essentially, from the starting node, you go to each of the neighboring nodes and figure out which one has the smallest known cost. From there, you move to its neighbors and check to figure out which one is the smallest cost as well. You then calculate the distance to this node by summing the cost of the edges leading from the beginning node. If the distance you find is less than the current recorded distance, you update this. Here's a visualization to demonstrate this. Our source is going to be 0, and we are going to find the path length to each of the nodes in this graph. So we start at this, we check each of its neighbors. From there, we find that the shortest distance is 1 to this neighbor. We then go from there to each of its neighbors, updating the distances as we go. So as we can see, the length to this one is 4 because we add the 3 and the 1, and we update this distance from 5 to 3 because we see we can take this path instead. Finally, we go to the next shortest, update that length, then check from here, but keep it the same because the length from this path would be greater than going from this path. Some applications of shortest path length algorithms include the traveling salesman problem, road mapping such as Google Maps or MapQuest, computer network traversal, and autonomous vehicles and devices. In this video provided by VT Autodrive, an autonomous vehicle design team here at Virginia Tech, we can see a visualization of how path planning algorithms guide autonomous vehicles. In the large window, we can see what is called a cost map, which essentially tells the car where it should and should not drive, with the pink area being completely off limits and the darker areas being less safe than the lighter area. With this data, an algorithm like Dijkstra's or A-star is then used to find the shortest path, which is sent to the actual controls of the vehicle. In the upper right-hand window, we can see the car actually following this given path.